All right, so we've already talked about how to find limits, but what we want to talk about here is like the specific types of justifications you need to write when you're doing a free response question. And in order to do this in a logical way, you have to know exactly what the definitions of some of these things are. Now, the first definition is actually a little loose. I call it, they always call it the intuitive definition. And like the proper definition of a limit is like really, really advanced and usually isn't even taught until you get to like higher levels of math in college, usually called like a real analysis class. But in calc, there's just this kind of intuitive idea. Usually it's explained by looking at a graph. So I'll just like kind of show an example here. But if I say the one-sided limit x approaches c plus of f of x, we say it exists if it approaches c from the right, but does not equal c, so just gets close to c without equaling c. F of x becomes arbitrarily close to a finite real number L. That's when we say a limit exists. The main point here is this word finite I want you to pay attention to. If we say the limit goes to infinity, that's going to be a specific way that a limit doesn't exist. But it's a very delicate detail because most people think, oh, when I write D and E, that's the only time a limit doesn't exist. But it's actually whenever a limit doesn't equal a number, that's when it doesn't exist. And that wording is important when you do justifications, because when you say a limit exists, you want to know exactly what you're meaning by that. So a little picture of this is, here's C and here's L. And a function might look like this, like x goes to c from the right. So if you start from the right, what it means is the closer and closer x gets to c, L will get closer and the y value will get closer and closer to L, okay? And so basically what this word arbitrarily close to means is if I start to the right of c, and you want, and then someone comes along and says, well, are you, like, if the limit is L, they would say, well, are you within 0.1 of L? And you're like, well, not now, but if I get closer to C on X, I can get within 0.1 of L. And then someone can come along arbitrarily and say, well, I'm going to say 0.01. And you can say, well, I'm not that close now, but if I get a little closer to C for X, then I can get within 0.01 of L. Does that make sense? So basically, arbitrary means if anybody gives you a number really close to L, you can get that close to it by tracing closer to C on the graph. So that's what that wordy definition means, and it's intuitive. And that's as good as we're going to do in you know, high school or first level calculus. And then like in later levels, there's a much more rigorous involved definition, but that's good enough for now. And then this is literally the same definition written out, except instead of approaching from the right, you approach from the left. So if the graph looked like that, I could get as close as I want to L by just tracing the graph, and from the left side, getting closer and closer to C. Okay, so that's what those mean. Probably in the practice of like getting problems right on the AP exam, I don't know how particularly helpful this definition is, other than just giving you a basic understanding of what's going on. This is actually like really important when it comes to justifications, though. If the two-sided limit x goes to c exists only if the one-sided limits exist, meaning they're finite, they don't go to infinity, and they're equal, okay? And then in this case, we would say, obviously, as we always do, that the limit x goes to c of f of x equals L, okay? As long as these, you know, exist and are equal. If they're equal to L, then if they're both equal to L, we say that this limit equals L. Now, this is just a very kind of high-level theoretical discussion of stuff you already know, right? Yeah, when the one-sided limits don't match, you know that the limit doesn't exist. And some people mix up the wording, though. They call this a one-sided limit, but this is two-sided because it depends on both sides. So it depends on two sides. I often write a plus minus there to remind students, like, you have to look at both sides to find that limit. All right, so keeping in mind that we only say that a limit exists, the word exists is only applied when the limit equals a finite real number. Then, really in these cases, even though we would write that, like, for instance, letter C, we could write that the limit as x goes to 3, since these match, equals infinity, it would still not count as existing, because infinity is like a type of not existing. And the reason for that, like, I think a nice way of remembering that is a limit exists when the function is getting closer and closer to a specific number. And when I go to infinity, the function might be going to 10, then 100, then 1,000, then 1,000,000, then 1,000,000,000. Now it's headed to infinity, but is it getting close to a specific number? No, it's like hitting a bunch of different numbers on its way to getting to infinity, which just means it's getting bigger and bigger and bigger. So these traditionally, A and B, most students would be able to tell me, or D and E, you would say this does not exist because those don't match. Ditto for B. A lot of people would think C exists, but actually D is the only one where it exists because those both match and equal a finite number. So there you could actually say that this exists. Whereas the infinity is a type of not existing. And that's a delicate detail that's important in justifications, because we're going to use the word exists and we're going to mean that specific thing. All right. Okay, all good? Okay. So, a limit doesn't exist for a ton of different reasons, but in AP Calculus, there are really 3 that they want you to be aware of. So the 3 reasons that a limit doesn't exist is because the one-sided limits are unequal. That's the one you're probably most familiar with. The one-sided limits are infinite. That's the one we just kind of brought up. And then the function oscillates near the limit. Most pre-calc students haven't seen this, and they put it on the AP exam just as there's really one specific example that they want you to be familiar with, just to show that, like, it's a little bit like there are examples beyond these 2 reasons. They don't show up a lot, but there are examples beyond these 2 reasons. I think that's what 3 is kind of for. So this first example says, well, at x equals 2, the limit does not exist because the one-sided limits are unequal. So let's just write out the calculations that support that to make sure you understand. So limit x goes to 2 plus of f of x. So if I start to the right of 2 and trace the graph allowing x to approach the value of 2 from the right, it is getting arbitrarily close to what number? The y value is getting close to what number?
5.
Good. And then if I approach 2 from the left, the y value is getting arbitrarily close as x approaches 2 to 2.
And I have a question really quick.
Yeah.
On the AP exam, would you write limit of f of x, or would you write limit of, like, whichever one is in the piecewise?
So you always want to start with f of x.
Okay.
And then if you want to, then you can simplify f of x to whichever piece it is.
Okay. Do you
But
have
it's,
to, or will you not be having to?
on a free response, I think what it's best to do is always start with the function they're asking about, and then simplify from there. You don't have to. If you do it in your head or whatever, I think that's fine. In terms of the one-sided limits, I believe the only justification that's really required is giving the answer.
Okay.
So it kind of goes back to that intuitive definition. That first definition of a one-sided limit is considered intuitive. So it doesn't require justification. It just requires giving the answer. But then once you build up those pieces, then you're required to justify with those pieces. Okay? So these 2 put together, okay, some people say, well, that's x goes to 2 plus, that's this way, x goes to 2 minus, that's this way. They would say limit as x goes to 2 is where the point is. And then they would say that's 4. Is that correct?
No.
No, because what a two-sided limit really means is it means combine these two, and then if they don't match, it does not exist. And often here, I like to use a bracket and a therefore, because that's logical. What you're saying is like, there are other ways of writing it. You can just write it below it, and that's fine. But I like it this way because I like logical justifications. Like, my logic is I just proved, and this is what justification is about. How do you prove that a limit doesn't exist? Well, you write what the one-sided limits are, and then that therefore is that little triangle. Therefore, that tells me that this limit doesn't exist. So rather than just writing this, I've written this, which proves it. Okay? So that's kind of the difference here, and that's how you would show a limit doesn't exist for the first reason. Okay?
4 would just be f of 2, right?
Exactly. So, is a nice comment. I was actually going to include that, and that's great. You saw it coming yourself. If we don't write limit, but we just write f of 2, that's what the point is referring to. So, you don't write limits to get the point, you just write f of 2, and that's what the point is. Now, sometimes the limit and the point match. Like if the graph looked like this, finding the limit would be equivalent to finding the point. And we're going to get to later, that's actually when a function's continuous, is when finding the limit and finding where the point is are the same exact thing. And that's when something's actually continuous. But when things are discontinuous, when you find the limit and you find the point, they'll be different. So when you find limit as x goes to 2 and you find f of 2, you'll get different answers when it's discontinuous. If it's continuous, they'll be the same answer.
Okay.
Cool. Next one. At x equals 3, the limit does not exist because the one-sided limits are infinite. So just notationally here, if I say limit x goes to 3 plus, of f of x, the other reason it's nice to just say f of x instead of the function is it takes less time. So what's nice is the proper way of doing it is the easier way of doing it, which is great. Yeah. So, So like I would just say like it's like that's the way they're going to always write it, and it's easier anyway. So go ahead and do that. So this is infinity, and then if you approach, that's this side. And then do you agree when you have a vertical asymptote, the one-sided limits are always going to be plus or minus infinity, and since it goes up on each side, they're infinity. Now, here, that means that the limit is x goes to 3 of f of x equals infinity, but that's considered a type of not existing. So I could say, so the limit does not exist. Now, since this is a specific type of not existing, we write that it equals infinity, but it still means that the limit does not exist. So if they ask you, like, does this limit exist, this would be the justification, okay? Now, this is just this really bizarre function. I really think the reason they put this in the class is just so you're familiar with this function, and there's a very similar one if you do cosine of 1 over x. This is just, I think, a very important example to be aware of, because I think most students think that the only ways a limit doesn't exist is if the one-sided limits don't match, or if one of the one-sided limits goes to infinity or negative infinity. Honestly, 99% of the time in examples, that's when limits don't exist. But they just want to like open your eyes that there are these bizarre functions that don't come up very often, that don't exist for a different reason. So with sine of 1 over x, you can see on the graph here, what happens with it is it oscillates between 1 and negative 1. Now, if it were sine of x, just sine of x, it would look like this, right? But when it's sine of 1 over x, it turns out that the oscillations get shorter and shorter in period. So do you see what's happening? Is it's bouncing between 1 and negative 1, but it's doing it faster and faster and faster. So the graph actually isn't solid here. What's happening is that the bouncing is getting so fast that just like a wheel turning, it looks solid because it's moving so fast. Does that make sense?
Yeah.
But as you approach 0, what's actually happening is you're bouncing at like an infinite speed back and forth between negative 1 and 1. And since it's bouncing between negative 1 and 1, is it getting close to a specific finite value? No, it's consistently like hitting values between -1 and 1, not getting close to any specific value. So here you would just say the limit does not exist. Or I would just say, you could also use limit notation. Limit as x goes to 0 of f of x does not exist due to oscillation. Okay? Now, honestly, I don't think this is going to come up a lot in solving problems. I haven't seen any on the AP exam or in the class. I just think for the intellectual standpoint, they want you to be aware of these examples so that you're aware of one example. And maybe there's others that I haven't thought of, but to me, these are like the main examples, sine or cosine of 1 over x, where you've got a limit not existing for kind of a totally different reason than the other reasons, okay? Super rare, but good to be aware of it. Now, the next set of definitions are going to be the most important for free response questions. So basically, they want you to be aware of what it means for a function to be continuous at a point. And then they want you to be aware of the three main types of discontinuities, which are called the removable discontinuity, the jump discontinuity, and then the discontinuity due to a vertical asymptote. And we want to make sure we have like very clear definitions for these. So f of x is continuous. The definition of a function being continuous at c is if the limit as x goes to c of f of x is the same as f of c. That's the official definition, the classical definition in calculus of what it means to be continuous. It's not exactly how I explained it to you in pre-calc. What I explained to you in pre-calc is I said, always do the three-step check, because if you know these three things, you always know the continuity or the type of discontinuity of the function at a point. So what I would say is find f of c, find the limit as x goes to c plus, and find the limit as x goes to c minus. And what I taught you last year is if all three of these equal the same number, we'll just call it L, then you've got a continuous function at that point. Okay? So do you remember me explaining it that way at any point? Yeah. So that's to me like the basic way is like if you know these three pieces of information, you know the continuity. So that's the way I described it. So let's see how like the way I taught it to you matches with the official proper definition. Well, if f of c equals L, that means that the point is actually at L. Agreed?
Yeah.
And then I don't know exactly what the graph looks like, but if I approach from the right or the left, I'm just starting randomly on the right or left because I don't know what the function actually looks like. As I get closer to c, the graph will get closer to L. And then that looks like a continuous graph. I could draw through it continuously without lifting my pencil, right? So that's what the graph in the three-step check that I taught you look like. How does that relate to this? Well, if these two are equal, doesn't that automatically mean that this is equal to L?
Yeah.
So basically, this is saying the equivalent thing, because if these two are equal, these two being equal is summarized by this existing, and then being equal to some value. And f of c has to be equal to a finite value. You can't have f of something equals infinity. So it's just implied that, like, basically, this is equivalent to this. But since this is the official definition, this is the one we're going to have to use when we write a justification. So I still like to start by finding these. These are always the computations I make. And then after I make them, I kind of put them together to satisfy the actual definition, which is like I put these together and say that the limit goes to L, and then I can say those are equal to each other. Now, when does a function have a removable discontinuity? Well, the way I taught this in pre-calc is the picture looks like this, and either there's a hole there so that the function's undefined at C, or the point is in like the wrong place. It's not where you would expect it to be. In this case, you would say like f of c, equals, we'll just call it k, which is not equal to L. Just like anything you want, really. And then limit is x goes to c plus of f of x would be L. And limit is x goes to c minus would be L. So from this picture, you can see how the three-step check works. If you find these three things, what's going to make a removable discontinuity was the limits match, but the function value does not. And that's the way I explained it in pre-calc, because I wanted to just, I wanted you to focus on these computations, and then say, when I do these computations, when I look at it, how do you immediately tell you've got a removable discontinuity? And that's how, okay? But then the official definition is this. So when you justify, you're going to have to talk about the official definition. So f has a removable discontinuity at c if this limit exists. Well, if these two matched, isn't that exactly what you need for this limit to exist? Because this just depends on those two matching. So that's just saying that these two match. It's another way of saying that. But the limit does not equal f of c, yes, because if this limit will equal, the two-sided limit will equal L, and then since this does not equal L, that's what makes it removable. So do you see the logical connection between doing the three-step computations and then this official definition? Cool.
Yeah.
Next two are the jump and the vertical asymptotes. So f of x has a jump discontinuity if the one-sided limits exist but are not equal to each other. What's interesting on this one is that actually where the point is completely irrelevant. I could put the dot here, or I could put it here, or anywhere, and it doesn't really matter. That's a jump either way, okay, in any regard. So what's going on here when you do your three-step check is it really doesn't matter what f of c is, okay? It could equal anything. But if you find that the two limits both exist, meaning they don't equal infinity, they equal finite values. So let's just call it L and K again. Okay. If the limits, when you do your three-step check, if the limits are unequal numbers, not infinity, but numbers, that's when you have a jump discontinuity. If one of them's infinity, that's when you're going to have a vertical asymptote, okay? But let's look at the official definition. We use the word exist, but we already talked about this. Exist means equals a finite number. So if these two exist but are unequal, doesn't really matter what's going on with f of c, that's when you know you have a jump discontinuity, okay? I usually just find f of c for consistency. I always find these three things. But if it turns out to be a jump, I don't even think you would be required to show that because it's not part of the definition of a jump. It's irrelevant what f of c equals when showing something has a jump. All right, next. F of x has a discontinuity due to a vertical asymptote at x equals c. Now, here's the thing. Different people might have different definitions of this, but I've looked in a couple of recent calculus textbooks, and they have and or. If either one-sided limit goes to either plus or minus infinity, you automatically count it as a discontinuity due to vertical asymptote.
And would you write that, like when you write the definition?
So, like, what I like to write is, when we get to the justification, we'll do an example. What I like to write is, f has a discontinuity due to vertical asymptote because, and then I just quote either one or both of the one-sided limits going to plus or minus infinity. And maybe they'd be positive infinity, maybe they'd be negative infinity, but like in a specific example, it won't be plus or minus. It'll be either plus or minus, and I do what it is in that specific example.
And would you do both, or?
Technically, I think by this definition, you would only need to do one of them, because as soon as one goes to infinity, but just in case your teacher's possibly using another definition, I might just list both if both happen to go to infinity. Okay. But by this definition, if we're taking this to be our definition, you would only have to state that one of them goes to infinity, and you'd be fine.
Okay.
So examples of this would be like this. And then another example that kind of goes to your point, this is the reason I did two of them, would be like maybe this goes to, let's do one that goes to negative infinity. Maybe this side would go to negative infinity, but it might be piecewise, and this function might just like be linear here. But I would still call this a discontinuity due to vertical asymptote because it goes to infinity on one side, according to this definition. And that's my best guess of what they precisely mean by definition, or by discontinuity due to vertical asymptote. Cool. So let's actually get to the important questions. These are the types of questions you're going to be actually solving and you're going to be graded on in Chapter 1. These next 4 examples. So here's the way I like to set up my justifications because I think it's most logical. I like to first do my computations, meaning I find f of 0, because it says it wants us to discuss the continuity of the function at 0. So I find f of 0, then I find x goes to 0 plus limit of f of x, and the limit is x goes to 0 minus of f of x. So I'm going to do these computations, and then once I've done them, I should know the answer. But then I'm going to relate those computations to the exact stated definition of what it means to be continuous, or removable, or jump, or vertical asymptote. All right. So f of 0, we're going to plug into this category because this is where x equals 0 exactly. So 0 minus 6 over 2 is negative 3. X goes to 0 plus, the way I like to do a piecewise limit, and maybe you can do this in your head, but this is, I think, the most proper way of showing it, is I would first state, well, if x is approaching 0 from the right, then you're going to use the definition of the function that's to the right of 0, which is this. And then, if you plug in 0, you get 0 over 0. That's an indeterminate form. And do you remember, we've already discussed how to find limits. If you get 0 over 0, you want to reshape the function. Agreed? Yeah. Okay. So I'm factoring, I'm canceling x. And then I get the limit as x goes to 0 plus of x minus 3. And that function I can just do by direct substitution. 0 minus 3 is one of the cases where you can just plug in and you're done. The limit doesn't go away until you actually plug in 0. Some people leave the limit out in these steps, like they fail to write limit there. And that's incorrect because this isn't just x minus 3, this is x minus 3 as x is getting close to 0. Okay? So on a free response, if you do a little bit of work in your head, on a multiple choice, if you do some work in your head, not a big deal. On a free response, you need to write the work properly and use proper notation.
So you do have to plug in there?
So in terms of the work, like
plug in the piecewise into the...
Like this step, I think, this step I think would be optional. Okay, but like you really need to show this work because if you just were to plug into this, you get 0 over 0, and that isn't even a defined number.
Yeah.
So then your work is just going off and it's illogical, where each of this work is I think, good. I think if you skip from here to here, it's fine because it's pretty clear that you're just canceling the x's there. But this is as good as I can think. For this one, I'm going to do something similar. Plug in to this definition now. And now when I plug in 0, it's not a special case. There's not 0 on the bottom, so I just get 0 minus over 2. Again, notice the limit disappears when I actually plug it in.
Yeah.
And then there's my answer. Okay. Now looking at this, all of them match. So what does that automatically mean?
That is continuous.
Continuous. And so if it were multiple choice, bubble continuous, move on. But if it's free response, we need to relate it to this definition. Does the actual official definition say that just all 3 of those have to match? No. It says that the limit as x goes to c of f of x has to equal f of c. So, since it involves the two-sided limit, we actually need to write that down. Because we have not written down the two-sided limit yet, agreed? So these two together, this time I'll just write it below it. Not a lot of room there. These two together, I can say, therefore, the limit as x goes to 0 of f of x is equal to negative 3. So I want that because that's involved. So that becomes part of my computation as I want to address what the two-sided limit is, because that's the way the official definitions are often set up. Okay? And then what I could do is I could say, oh, then I'm going to use the official definition. So f is continuous because, at x equals 0, you have to be specific. So it's not just continuous everywhere, it's at a specific point that you're proving. So f is continuous at x equals 0 because, and then you just basically quote the definition. The limit as x goes to 0 of f of x is equal to f of 0. And do you see how I wrote down the exact official definition? And the reason this is justified is f of 0 is -3, and this is -3, which I showed before. So whenever you write, because you did your computations at the start, when you write that, it is assumed that you're just saying -3 equals -3. You don't have to write that, but do you see why that's justified? If I just wrote this, it wouldn't be justified because I wouldn't have found these to prove that they're equal. But I can state that they're equal because I proved that they're both -3 up here. Some teachers show their work like this. They say limit as x goes to 0 of f of x equals -3, and that equals -3, which is also f of 0. And they find this, and they do the computation here, and they find this, and they do these long comparisons. I like to keep my computations separate. I like to do them up here instead of do it while I'm justifying. So I like to compute then justify. It's not wrong to do this, but I just think big long equations like that are a little confusing for me, so I prefer this way. But if you'd like to do it that way, or if your teacher does it that way, that's not wrong. I'm just going to do it this way. Computations here, then state the definition below, okay? Or state the justification, which is basically saying, this satisfies the definition of the function being continuous. All right, and that's how pretty much you're going to prove a function is continuous on a free response and get full credit every time. So that's a really important example. I'd honestly be shocked if the majority of calc teachers didn't give a question similar to that on a continuity test. Obviously, these specifics will change, but they're going to want you to prove a function is continuous, and that's how you're going to do it. Okay, next one says show that it's continuous or classify the type of discontinuity. So it might be continuous, might not be. Let's do our computations. So let's find f of 1. This time it's at 1, so I'm going to do the 3-step check at 1. Limit x goes to 1 plus, and limit x goes to 1 minus. So f of 1, I plug into the top function because that's where the function, because x is equal to 1 there. So I'll plug in 1 squared plus 1, which is 2. 1 plus, I'll still use that top definition. And then this isn't really a special case where I have to do any reshaping or anything. I just directly plug in. We've studied how to do limits. That's going to be 2. And then the third one, we're going to do cosine of pi x. And then, I know it's 1 minus, but you always just start by plugging in 1. Not -1, it's just 1, right? Mm-hmm. And since that's not any kind of special case that we need to deal with, that you can just solve this with direct substitution, the cosine of pi is just -1. Now, this isn't removable. A removable is where the limits match. What is it when the limits don't match? Jump. When they don't match but are numbers, they exist, right? So, generally here with my computations, I still like to say, therefore, the limit as x goes to 1 of f of x does not exist. Just because I like to be in the habit of always finding all of these. But to be honest, you wouldn't really need this because the definition of a jump is that the one-sided limits exist but are not equal. Does that make sense? Okay. And then you can either write out with symbols or you can write out with words. It really doesn't matter as long as you're addressing the specific official definition of a jump. The official definition is f has a jump discontinuity if the one-sided limits exist but are unequal to each other. Okay? So I'm just going to phrase this a slightly different way, but I'm going to say exactly the same official definition. So I'm going to say f has a jump discontinuity at x equals 1 because the one-sided limits at x equals 1 exist, but the limit as x goes to 1 plus of f of x does not equal the limit as x goes to 1 minus of f of x. Or I think you could say that in words and it would still be justification. You would say the one-sided limits at 1 exist, but they are not equal to one another. And that would be saying it just as well. It's not about, I think sometimes when teachers are trying to get everybody on board and get the right answer to a type of question, they will sometimes say like, we'll always write it this way, because they know as long as you write it the way they're showing you, you get it right. But I would like you to really understand the logic and understand, you can say it in a couple different ways, but as long as the logic is clear and you're relating it to the official definition, that you got it down. So if your teacher phrases it differently, fine, not a big deal. You can do that. But I've related it to the official actual definition of a jump. I didn't just find them and say it's a jump. I said why it's a jump by stating what the definition of a jump actually is. All right, next one. Okay, once again, let's just start by doing our computations and then we'll figure out whether it's continuous or not. So this is a 2, so I'm going to do 3-step check at 2. F of 2, limit x goes to 2 plus of f of x, and limit as x goes to 2 minus of f of x. So f of 2 is when x actually equals exactly 2. When x equals exactly 2, what does the function say? 6. If x does not equal 2, another way of saying not equal 2 is you're either greater than 2 or less than 2, right?
Yeah.
So that basically covers 2 categories is what's going on there. So here, f of x, we'll use this definition. And that's 0 over 0. So I'll reshape. And then what's left after reshaping, I can just do by plugging in. So that's going to be 4. And then here's the thing, and I'll talk about this in just a second, but your work is pretty much going to be the same for x goes to 2 minus because it's the same definition. So on that, I'm going to skip ahead and say it's 4 because I already showed the reshaping there. Okay? So I think it's probably okay to say that you understand that limit in the same way. If you want to be really careful, you can show your work there. Now, what is this? What type of discontinuity is this? They're not all equal, but the limits are equal. What is that going to be? That's going to be a removable. So for a removable, you can't just say, well, the limits match, but the function value doesn't. I know that's like the way I describe it, but the official definition, going back, is that the two-sided limit exists, but it does not equal the function value. So I better address that two-sided limit, right? So I better take both of these and say, well, therefore, the two-sided limit as x goes to 2 of f of x, equals 4. Which, when I write that, it implies that it exists. And then I can write the definition. F has a removable discontinuity at x equals 2 because the limit as x approaches 2 of f of x exists And once again, where did we show that? We showed it right there. When we say a number equals a 0, that's the justification for, or a limit equals a finite number. You know, that is equivalent to saying it exists, because the limit as x goes to 2 of f of x exists, but does not equal f of 2. Notice I didn't phrase it exactly the way I did. I didn't say that this and use the does not equal symbol f of 2. I just wrote it in words. But the logic is the same. I'm saying the same thing. Whether it's symbol or words, I'm saying the same thing. This limit exists, but it's not equal to f of 2. Do you see my point there?
Yeah.
I could have also written limit x goes to 2 of f of x does not equal 2 in symbols like this. Mm-hmm. Same thing though, okay? That is the exact definition of removable discontinuity. Now, do you see here how for x goes to 2 minus and 2 plus, the limit was the same definition? This works great, but if you want a shortcut, you would be absolutely fine just saying f of 2 equals 6, and then finding the limit as x goes to 2 of f of x. Because when x approaches 2 from both the right and left, it's going to have the same definition. And I could fill in that detail and say that that's equal to 4. And I wouldn't actually have to do the one-sided limit separately. Do you see how I can show that limit computation because it's the same?
Yeah.
That's a shortcut. Not necessary. Some people like the rhythm and the music of doing the 3 all at the same time. Step 1, step 2, step 3. I know the continuity. I often teach it that way to just emphasize the consistency of doing that. But that is an available shortcut if finding the limit from the right and left is equivalent, like it is in this example, okay?
Okay.
Cool. All right, so not required, just a shortcut. Show that, and then of course you would still, after doing this shortcut, I should say, then after this you would still then go back and state this, because that's required for your justification. It's just in your computations you could show it that way. All right, now the last example here on continuity says, show that f of x is continuous at x of 3, or classify, just like the others. So now we're going to do 3. So f of 3. Now, limits can go to infinity, but function values are either numbers or they don't exist, okay? So f of 3 would be in this category, greater than -1, but when I plug it in, it makes the bottom 0. So that's a d and e automatically. And I don't like to write d and e because d and e really isn't a number. I like to just write, a lot of people write equals d and e, but it's not equal to d and e in my opinion. It's just like f of 3 does not exist. I'm saying a sentence basically. And then I'll do the one-sided limits. Now, with limits, when you plug in and get 1 over 0, so when I plug in 3, I get 1 over 0. When the numerator is non-zero and the denominator is 0, I often call this the k over 0 case, or some people write non-zero over 0 case. You know that the one-sided limits can only equal one of two things. Do you remember what they are?
Infinity or negative infinity.
Exactly. So in this case, I'm going to get infinity, because if I plug in, the way you do is you estimate. If I estimate the limit by plugging in 3.1, I get a positive value, so it's infinity. And I end up getting the same thing for 3 minus. This is true for rational functions, I should mention. But if I plug in 2.9 to estimate this limit, because 2.9 minus 3 is negative, but because it's squared, you still get a positive. So this is infinity as well. So I'll go ahead and address the two-sided limit just out of having good habits. I actually don't think it's necessary on this one, because the one-sided limit, as soon as like one of those infinities pop up, pretty much game over by the definition I gave you. It's going to be that. But just to be a little bit more thorough, I'm going to also address the two-sided limit. And just because you're being asked about f of x, I do think it's a good idea if you just start. I kind of skipped this step, but I think it would probably be good to address, well, that's f of x, which does turn into this. limit as x goes to 3 of f of x equals infinity. Okay. All right. Now what I'm going to say is f has a discontinuity due to a vertical asymptote at x equals 3 because, okay, and then I could write these out, but I'm just going to write it in words. The one-sided limits are infinity. You could say the one-sided limits are infinity and negative infinity, but your computations are right there above. So anything you state here, you don't have to restate. It's clear from above, okay? And on the AP exam, if I write like A equals 5.2, this often happens on calculator problems. If A is some ugly decimal, if I write that at the top, I don't have to keep writing that ugly decimal in my work. I can just say A every time I'm writing it. And it's a very common official way. If you write that, you know, something equals a number, you can assume that that's the case for the rest of the problem. All right? Okay.